Okay, so this homework assignment, among other things, gave you some problems where you had to write the equation of the rational function from the graph. And someone had asked in one of the Zooms last week, I think it's a very good possible candidate for your upcoming test. So I thought you guys might want to look at some of these together. So essentially what we're going to be doing is using our Schrade steps in reverse. And so some of the characteristics that you might notice about this graph is there are two vertical asymptotes in the graph. They didn't actually draw them in, but we can tell where they are because of the breaks in the graph. And we have one of them at x is negative 1. And we have one of them at x is equal to 2. But I want you to notice these two branches head the same direction at that vertical asymptote, which we didn't actually graph, but we did talk about numerous times. And that means that occurs twice. It's what we call a multiplicity from your polynomial unit, but it simply means it occurs twice. And so it's going to be a squared factor. This would be the t-step of your Schrade, okay? And so that's what that's telling us. Then we also notice that we have an x-intercept, and of course that's also the y-intercept. So we have one root on this graph at x equals 0. And we can tell that we have a horizontal asymptote at y equals 0 because the ends of the graph are very, very flat and very, very close to 0. And so, of course, this would be the e step of Schrade. And that just tells us that we need to make sure we end up with a bottom-heavy equation once we're done. Okay, so all we do is we just start plugging in these characteristics into a rational function. So we know that vertical asymptotes occur from the denominator. So x equals negative 1 means that x plus 1 is in the denominator. X equals positive 2 excuse me, means that x minus 2 is also in the denominator. And then it occurs twice. The branches do move together there, so it would be a squared factor in the denominator. And we only have one root at x equals 0, which means we must just have an x by itself in the numerator because that's where roots come from. And sure enough, we do confirm that we have a bottom-heavy equation already, so this equation would have a horizontal asymptote at y equals 0. And that's it. The equation would be done. Okay? So then number 12 is very similar, but it also has an additional characteristic. Okay, so same kind of process. We see that we have two vertical asymptotes again. We have two physical breaks in our graph. One of them is at x equals positive 1. And then one of them is at x equals negative 2. And once again, the two branches move together. So this would be the t-step of Schrade. That factor in the denominator is going to be squared because of that vertical asymptote and the behavior around it. Our horizontal asymptote is still y equals 0 because the edges of your graph are still getting flat and very close to 0. So once again, we need to make sure we have a bottom-heavy equation. And then we have an x-intercept, which is once again also our y-intercept at x equals 0. But what I want you to notice is that we don't actually cross the x-axis there. We bounce on the x-axis, or we are tangent to the x-axis. So this would also be the t-step. If you remember your polynomial unit, this is what happens when a root occurs twice. Okay? And so the only real difference in our equation this time is that we're going to have x plus 2 in the denominator, and it would be squared. So we still have a squared factor in the denominator. We would have x minus 1 for the other vertical asymptote. And then this root occurs twice, which is what causes that bounce. And so the x that's in the numerator would also have to be squared. So if you look at this equation, this is still bottom heavy. It would still have a horizontal asymptote at y equals 0 because you do have a quadratic on top and you do have a cubic on bottom. So it is still bottom heavy. And so that takes into account the horizontal asymptote. Okay, and then the last two problems that I thought you guys might want to look at are the ones that also throw in oblique asymptotes. So of course these will work differently. So we start the process the same. This time they actually did draw in the vertical asymptotes. So we have one vertical asymptote on each of these final graphs. This one occurs at x equals 3. Okay, we see that we have two x-intercepts. We have two roots in our R step because they actually did put physical dots there. And so we see that we have one at -2 and one at +2. You can see that there is a y-intercept, but they did not actually put a dot there. It looks like it's at about 1/2, but you can't confirm that. So you would kind of have this question mark next to it, and you can't use it as a concrete piece of information to write the equation. But what you can use is the oblique asymptote. So if you look at the oblique asymptote that they drew into the graph, it is a line. Okay, the y-intercept for that line is at +1. And the slope of that line, if you choose any 2 points, like these 2 points right here on that line, it has a slope of 1/3. So the equation of the oblique asymptote is 1/3 x plus 1. Now there are a lot of ways to account for that in the equation, but what I'm going to do is I'm going to start the equation the way we did on 11 and 12, and then I'm going to show you how I personally account for the oblique asymptote. But like I said, there's lots of ways that you can go about doing it, okay? So here's the initial setup for my equation. I have two roots at +2 and -2. So I know I'm going to have an x plus 2 and an x minus 2 in the numerator. I know I have a vertical asymptote at x equals 3. So I'm going to have an x minus 3 in the denominator. And that means I've got a top-heavy equation. I have a quadratic on top and a linear on bottom. So it is top-heavy, but I need to make sure that my oblique asymptote is correct. So I think about how would I have found the oblique asymptote if I was working this problem the other direction. And the way that we did it is we would have put a 3 in the box to set up a synthetic division problem. We would have set up the coefficients to the quadratic to the right of that, and we would have run through our synthetic division. Well, in this case, what we know is this time we know the answer that would pop up down here. It's going to be the equation for that oblique asymptote. So that 1/3 would have to show up as the leading term of our linear equation, and the +1 would have to show up. This remainder that would be right here wouldn't be important anyway. It doesn't matter what that would have been because we would have thrown it out anyway. Well, in synthetic division, whatever number you see right here literally carried straight down from right there. And so what that means is that this quadratic that's up here in my numerator, it needs to have a leading coefficient of 1/3. And so that there would need to be a 1/3 up in there distributing through it. Okay? And then the only other thing I would need to check, and you always want to check it, it almost always works out, okay? But you would need to check this, is you would need to make sure that you get the correct number right here if you did that, okay? So this quadratic right here, I don't have it multiplied out, but if I did, it would have been x squared minus 4. It would have been a difference of 2 squares. With the coefficient of 1/3 distributed through there, it would have been 1/3 x squared, no linear term, and then minus 4/3. So those would have been the numbers that would have been up here in my synthetic division problem. And what I want to do is I want to check to make sure that when I do the synthetic division and I multiply and then add down, I get the correct number right there. So if I took this 1/3 and I multiplied it by the 3 that's out here, sure enough, I would get a 1. And when I add down, I would get the correct number right there for the final part of my oblique asymptote. So what that does is it confirms, let me switch colors here, that this quadratic in my numerator simply needs a coefficient of 1/3 distributed through there. Now I will tell you that most math teachers, most math textbooks will not leave an equation with a fraction embedded in the numerator or denominator like this. So what most of us, math teachers, math textbooks, what we do is we simply would have relocated that number. So what I mean by that is, instead of, I'm too close to the top. Instead of having 1/3 x plus 2, x minus 2 over x minus 3, what we would do instead is we would have the x plus 2, the x minus 2, and the x minus 3. And instead of having a 1/3 up here, we would have put a 3 down here. And the logic for that is that it is a simplified version of the equation. You don't have embedded fractions in it. And multiplying times 1/3 in the numerator is equal to, or the same thing as, dividing by 3, which means you would have a 3 in the denominator. So it's just a rewritten version of the equation. And that was the answer that they showed you on the answer key when we checked this, when you guys were assigned odds all those weeks ago. So the final problem, number 16, will work out very similarly to that. Okay. So same kind of process. If you have not already tried these practice problems for yourselves, I would suggest you pause the video now and you actually try number 16 for yourself. Just give it a shot. And then when you're ready, you can come back and you can see that we have a vertical asymptote at x equals -1. So that would give me an x plus 1 in my denominator. I have 2 roots, or x-intercepts, at x equals 2 and at x equals 6. Once again, it looks like I think I can tell where my y-intercept is, but they did not put a dot on it, and so I cannot definitively say where my y-intercept is. So what I would use last then is the equation for the oblique asymptote. And once again, this oblique asymptote has an equation of 1/3 x, but this time the y-intercept is down at -3. Okay, so if I put my 2 roots into the numerator, I have x minus 2, x minus 6. Once again, if I was going about this the other direction, the way that we did most of our problems, I would have set up a synthetic division problem with -1 in the box. Okay, the coefficients for the quadratic to the right, and I would have had the equation for my oblique asymptote as my answer down at the bottom. So I would have had this 1/3 for the 1/3 x, and then a -3 as the equation for my oblique asymptote as my answer. And once again, this 1/3 would have come straight from here. So it looks like there should be a 1/3 in this numerator with that quadratic again. And once again, you always want to check this. Okay, guys? So, and I realize it's probably being overly cautious, but we always recommend that you check any assumptions that you are making. Okay, so we assume that everything else would work out. So I'm actually going to check it. So this quadratic right here, if I FOILed it out, it would be x squared minus 8x plus 12. If I then took that 1/3 and distributed it through, it would have been a 1/3 x squared minus 8/3 x plus 4. Okay, and so then what I want to do is I want to check to make sure the synthetic division works out correctly. So if I have my synthetic division set up like this, I need to confirm that I do in fact get a -3 right here. So 1/3 times -1 would have been -1/3. Add down, and you would have gotten -9/3, which sure enough is -3. And so we know that that coefficient of 1/3 is the appropriate and correct coefficient for that quadratic. And then our last step, once again, is you will usually not see us leave a 1/3 even if the 1/3 was on bottom, you guys, we still would have rewritten it. We don't leave embedded fractions in our answers. And so we would more than likely write it as x minus 2, x minus 6, and then put a 3 in the denominator with the x plus 1. And that would be the answer for that rational function. Okay, so I hope you guys are feeling better about your rational functions in the other sections in this unit, and hopefully I'll see you guys on Zoom again soon before we take our test.